Okay. This is your writing or no?
No.
Oh,
Not sure what that.
are you going to use the blackboard?
Okay.
Are you using the blackboard?
No. Maybe just for some scheme, but I will just, if I need it, I will use it.
What's this?
It's like a complex analysis, I guess.
Yeah. That's all. I have a bunch of
Already? All right, so everyone, thank you for coming to the lecture. And so today I'm going to talk a little bit about magnetic tunnel junctions and magnetic tunnel and magnetoresistance. And then tomorrow I will talk a little bit about superconductivity. So just to continue a little bit what we had in the previous class. So in the previous class we have this band structure of the semiconductors in plane semiconductors, and we saw that we can build a basis, and with this basis we can build an A by A Hamiltonian describing these A bands. So remember I have 4 bands here, but each of them you have to spin, so there are 4 A bands, and then by downfolding these bands we got into a spin-orbit coupling. And we were looking at the ways of breaking the spin degeneracy. If we want to use a spin, we have to distinguish them. So we need to break spin degeneracy. So according to type reversal symmetry, so you will have this relation for the energies. Sure?
I mean, if this is so far.
Just because the cable, okay.
The cable can extend.
Okay. I think it's okay. All right. Okay, so time reversal symmetry requires this equal, the energy at K spin up goes to energy minus K spin down, because time reversal symmetry inverts the K minus K and flip the spin. And on the other hand, if we have inversion symmetry, means K goes to minus K, and if the system is invariant to this inversion symmetry, then we should have these relations. Okay. And if we combine these 2 relations, we will have a spin degeneracy. So the way to break the spin degeneracy, we need to break one of these conditions, or both of them, right? So one will be to break the time reversal symmetry, and this we know we can do it with a magnetic field or with an exchange field. And the other will be to break the inversion symmetry, which is a little bit more subtle. And we actually, in the previous class, we analyzed these cases in which we have system with structure inversion asymmetry and how these generate spin-orbit coupling. And specifically, we analyze this, how the Rajah spin-orbit coupling emerges in these systems. So we have several of these systems which the inversion symmetry of the structure is broken around this C direction, right? So we have the case of this 2-dimensional electron gas forming a quantum well, and we saw that we can write an effective Hamiltonian to describe the subbands in this quantum well, which is given by this expression here, where this term here describes the Rajah spin-orbit coupling. And we saw also that is actually a very large, in comparison to the vacuum or to the atomic spin-orbit coupling. So the atomic spin-orbit coupling is very small because half a factor of 1/c squared. But the Rajah spin-orbit coupling is not necessarily small, actually, because we have this lambda. We have this expression in the previous lecture, so I'm not writing here, but the lambda depends on the parameters of this system. So there is no 1/c squared for this lambda. So alpha, the Rajah parameter, can be several order of magnitudes larger than the atomic one. So it makes possible then to measure these effects in real materials. The other thing is that if we apply a magnetic field, these here are the wave functions in this quantum well. So we can push the wave function to the left or to the right, in dependence of the direction of this electric field. And then we can pick more information about this potential here, this jump in the potential, or the other side. So we can control the size of alpha by applying an electric field. So it gives us an electric mean of controlling the alpha parameter, which is also something very useful because it's very difficult to control things at small scale with magnetic field, but it's easier to do it with electric fields. So we also look at the bands. So this structure inversion asymmetry induced Rashba band. So essentially the dispersion corresponding to this Hamiltonian. So you get, so remember we have, so if we have spin degeneracy, we have two parabolas, one on the top of each other. If I have exchange field, the parabolas are shifted vertically. If we have spin orbit coupling like Rashba, the parabolas are shifted horizontally. So essentially I get here so you can see one of these parabola here and the other here. And of course, in the system is rotational invariance, you get these two paraboloids.
Which is
Sorry?
Which is vertical, which is horizontal.
So horizontal I mean like so if I have a spin degeneracy, so I have these two bands. They are parabolic but on the top of each other because they have the same energy, the two spins. If I put an exchange field, well, they are split. So one of, let's say, spin down goes up and a spin up go down, let's say. Okay? And this is equal to this exchange field, this difference. Now, if I have Rashba spin orbit coupling, then instead of shifting the parabolas vertically, so they will shift horizontally. Okay, so you will have something like this. So this one of these parabolas shift to the right. I'll just put it like that, and the other to the left. Let's put it like that. And what you see, this is just the rotation of this, because this is for a given, let's say, a given direction of k. But you have k.
This is because of what?
This is because Rashba
Okay.
spin orbit coupling give you this, okay, which is what I have in here. Okay. All right. So now, if you look at the spin orientation, so you can also calculate the spin orientation for different values of k. So you can calculate the eigenvalues of this problem. So it's just a 2x2 matrix because you have just Pauli matrices. And you can get the eigenvectors of this and calculate the expectation values of the spin. So you can see the spin vector in which direction is pointing. And what you will find is that they are log, perpendicularly log to the momentum. Okay? So like you can see here in this. So if I put, kx, let's say, in this direction, so the spin will be perpendicular to that. So in whatever direction I choose, spin will be perpendicular to the direction of k. Okay? So one of the things here also is that these have a, this symmetry, C infinity. It means it have an axis of rotation in which you can make any rotation will bring the system, will keep the system unchanged. So have a rotational invariance around rotations in the plane. So you see, if you, whatever you do, you can rotate these Fermi contours as you want, you will get always the same. Okay, that's essentially the symmetry of this Rajah spin-orbit coupling. The other thing is that you see the electron velocity will also depend on the spin in that case. So the velocity is just the derivative of the Hamiltonian with respect to the momentum. And if you take this Hamiltonian and you derive here with respect to the momentum, you will get this expression for the velocities, meaning that you will get an extra term here that depend on the Pauli matrix, depend on spin. This is very important for the so-called anomalous Hall effect and spin Hall effect. I don't have time to talk about this in this course, but this extra term here gives contribution to the anomalous Hall effect and spin Hall effect. All right, so till now we have, we have this system in which the inversion is broken because, well, I'm building my structure in such a way. But we also saw in the previous class that even in the bulk, even if there is no heterostructure or anything, you just have one material, you still may have lack of inversion symmetry. And this was particularly valid for the thin-blende semiconductors. So this is the structure of the thin-blende semiconductors. And typically, if it was diamond, you would have this point here like inversion, a point of inversion symmetry. But you can see that because now you have, in this lattice A and B, you have different atoms, gallium and arsenide. When you make the inversion, so A goes to B prime and B goes to A prime, but they have different atoms, so you don't get the same. So these structures, thin-blende structures, lack bulk inversion symmetry. Even if the structure is symmetric, the bulk itself lacks this symmetry. So if you are breaking inversion symmetry, you should also have a spin-orbit coupling related to this breaking of symmetry. Now, to get this one is a little bit more complicated, but it's the same procedure we did for the case of Rajah. So the only thing is that we need to get more bands to get these effects, okay? So before we have 8 bands, now we have to go to 14 bands. So we have to add these other conduction bands. So then you have a basis which is 14 by 14, you get a Hamiltonian that is 14 by 14, you have to downfold it. Exactly the same procedure we did for the other case with 8 bands, but of course it's more involved because it's a huge Hamiltonian. And so you get very long expressions. You can go to the Spintronics review that I gave at the beginning if you want to see all these expressions. So I just will avoid the exact expressions, but I will tell you what is the form of this spin-orbit coupling. This spin-orbit coupling that is induced by the bulk inversion asymmetry is typically called Dresselhaus spin-orbit coupling because it was introduced by Mildred Dresselhaus, an American physicist. So there is a difference between Rajah. So we saw that Rajah is rotational invariant. For the case of the Dresselhaus, we will see that it's not rotational invariant. So if I give the Hamiltonian, this Hamiltonian, I don't have to specify any crystallographic axis because, well, it doesn't matter, it's just invariant, right? For all crystallographic axes, it will be the same. But when I write the Dresselhaus spin-orbit coupling, I should specify the axis because it is not the same if you took different reference axes. So what I'm going to write here, assume this reference axis. So my x direction is along the 1, 0, 0 direction, y around 0, 1, 0, and z around 0, 0, 1. And this is what you get from this bulk inversion asymmetry induced spin-orbit coupling. So you get 2 contributions. One contribution you can write it like this. So you have a parameter here, gamma z. Before we have this lambda z. Gamma z is just a parameter that depends on these band parameters. And if you have only one system, well, this is a constant because you have just one material. If you have different materials, then it depends on the position, right, on this z. Okay, so in the plane, so if you have only one you have a quantum well and you have only one subband occupied, you can make the average of this Hamiltonian, and you will get essentially this term here after average. So this beta is essentially the average of this term here. Beta 1 is the average of this one, and beta 2 the average of this one. Okay. So these are parameters, and you can calculate these parameters if you know the band parameter for the material. So if gamma is constant, so you see what you get here, this squared, this c squared is like the momentum squared, right? To a factor of minus 1. And so all this dc, all the derivative with respect to c is like the momentum in c direction. So you can actually rewrite the Hamiltonian in this form if gamma is constant. So this is probably the most common form that you will find in the books. And you see is Rashba is of first order in momentum, it's linear in momentum. But Dresselhaus is cubic in momentum. So Rashba, if you go in higher order, so you will get also third order in momentum. But we keep the lowest order, which is linear. But for Dresselhaus, the lowest order is already cubic, okay? So any question?
How does Hamiltonian be written?
Sorry?
How does the Hamiltonian be written in this form? How the derivation?
How to derive this? The same way I did it for the alpha. So you have, again, so you have a basis now, is this basis with more bands. So I have more bands now. I have 14. Before I have 8 by 8. So you build the Hamiltonian in this basis. So the Hamiltonian contains the kinetic energy, the periodic potential of the lattice, and the spin-orbit coupling, the atomic spin-orbit coupling. You build the matrix elements of this Hamiltonian with this basis, and you get a 14 by 14 Hamiltonian. And now from this 14 by 14, you downfold this Hamiltonian so that you go only to this superspace of this gamma 6 conduction band, because it's the more relevant for us. You know? And it's a lot of, I skip all this, it's a lot of math and so on. I just give you the final result, okay? Okay, so what I can do if I have a confinement, let's say in the C direction, I can actually make the average over C, and then instead of, let's say here, I can make the average over C of this of the Dresselhaus Hamiltonian of these two terms, and I get into this. And you see, I have an order here which is I call it linear Dresselhaus spin-orbit coupling, which appear like it's linear in P, but it's actually not linear because you have this second order, and this P is PC squared, which is in here, but I made the average and I put this PC squared like an average in beta. Okay, so in a way I'm linearizing this cubic term and make it linear. Okay. Now if the Fermi energy is low, so this actually will give you the higher contribution. Okay, because this will give you just higher order correction. So up to linear terms, then you have the Hamiltonian. If you have a system which have both structure inversion asymmetry and bulk inversion asymmetry, you will have this Hamiltonian with this Rashba spin-orbit coupling and this Dresselhaus spin-orbit coupling, or linearized Dresselhaus spin-orbit coupling. Again, so one have to be careful with the reference axis here. Again, the reference axis here where x is along 1, 0, 0, y is along 0, 1, 0, and z along 0, 0, 1. And this is because if you change the reference axis, so this is going to change. Rashba will stay the same because it's rotational invariant, but this will change. Okay. So how does it look? The spectrum now, the Fermi contours. and the spin orientation of these Fermi contours in the different situations. Let's say you have only Rajva, well, we know we have this, like before. If we have only Dresselhaus, so you see the spins, make a sort of like a texture here. So they are not always perpendicular to the momentum. Okay. And if you have both of them, Rajva and Dresselhaus, then the contours are not, are not circular anymore. So they start to look like these contours here, which, Now there is a special situation when alpha is equal beta. When the strain of this Dresselhaus is the same like the strain of the Rajva spin orbit coupling. And in this situation, what you get here, what you get for the contours is what I have here. So you get these two circles. And here, when you have both of them and they are different, so you don't have, the spin is essentially forming a texture, so it's just rotating in many different directions. So it depends on K, it's always changing. But when you are in this specific direction, alpha equal beta, you just get two orientations of a spin, just these two directions. This makes it very special case, and there are some textures that appear in there, which are called persistent spin helix, which have a long lifetime. But I'm not going to talk about this. It's just a curiosity. So just keep in mind that this is a very special situation, alpha equal beta. Now I can plot the spin orbit field. What I call the spin orbit field is the following. So I can, you see this, all of this is just P with sigma, and I can create a vector, so I can rewrite this spin orbit coupling in this form. Some vector W times sigma, or the dot product of sigma. And this W is what I call the spin orbit field. It is, you have a sigma splitting, you have B dot sigma. Well, I don't have B because I don't have magnetic field. I have W, which is play the role of this spin orbit field. And if you look at this, at the form that I have here for this spin orbit coupling, so you can easily realize that this spin orbit field, when you have Rajva and Dresselhaus, it will look like this vector here. Okay. Now, if you plot the absolute value of this spin orbit field divided by K parallel, and K parallel is just the square root of Kx squared plus Ky squared, you get these two situations. So you can make this plot, and you get this 8 if alpha is larger than beta, or this other 8 if alpha is smaller than beta. All right? So any question? Yes?
So the plot there showing the country, the field, is the spin orbital field strength, or?
The plots?
Yeah.
The plots are the absolute value of the field divided by K parallel. Normalized to K parallel. Okay.
So physically, how do we understand that?
What I understand what?
No, yeah.
So you have this spin orbit field, right?
Yes.
And this will create some things when you do so. And one of the things that it will create is anisotropy. But you see, if you look at this, at the strength of this field, it's not the same. It depends on the. So you have only Rajva, it will be isotropic. If you have only Dresselhaus, it will be isotropic. But when you have both of them, you have like this 8, and you see, let's say, this spin orbit field around a strength around 110 is different than around -110. Okay. I just want to show that this, and it's related to something that I will show you later on. I just want to show that it is anisotropic. And actually the anisotropy, this axis of symmetry, can be flipped when you change the relation between the strength of Rajva and Dresselhaus spin orbit coupling. So if alpha is larger than beta, you get this symmetry axis around 110. Otherwise, you get it around minus 110. Okay? So with this, I conclude the things about the spin orbit coupling, and I will go now to the magnetic tunnel junction.
So
Yes?
this C part is alpha larger than beta. The C part.
The C part, yes.
Oh.
Yeah. Otherwise, it just will flip to the... So. All right, so any further question? Okay, so for the magnetic tunnel junctions, so I will talk a little bit about what are these magnetic tunnel junctions, what they are useful for, and how to model them. So I will discuss a couple of models. Maybe, all this math is, I have some notes and so on, but I probably will skip some of the math, just give you more or less the idea of these models. And then I will present a brief discussion about the tunneling and isotropic magnetic resistance. All right, so there are two phenomena that are very similar but different, okay? So one of them is called the GMR, or giant magnetic resistance. So both of them are actually included in what is called spin valves. So a spin valve is just a device that will allow you to, some of the current to go through easily and the other one no, okay? So you have a layer structure like this one, so you have a ferromagnet, you have a normal metal, and you have a ferromagnet, so everything here is a metal, okay? In that case, what you can find is actually that if you measure the resistance, when the magnetization in these two layers is parallel, and you measure the resistance when they are anti-parallel, they are going to be different, okay? This was what was discovered by Albert Fehr and Peter Grunberg independently of each other, and they got the Nobel Prize in 1988 for this discovery. So in 1988 they discovered it. In 1988 they discovered this in the lab, and in 1997 it was already in use. So in these magnetic hard drives. So it's one of these phenomena that have been going from fundamental research in the lab to real applications in a very short period of time. 10 years, less than 10 years, or about 10 years is a short time for something fundamental to go to application nowadays, everyday's application. Now, so I won't discuss what is the physics about the giant magnetic resistance. I will instead talk about the tunneling magnetic resistance, which is somewhat similar. The difference is that instead of having this normal metal in the middle, I will have an insulator or a semiconductor. So it's something that will build a barrier, a potential barrier between these two ferromagnets. And so here again, so if the configuration, you are in this parallel configuration, the two magnetic layers have the same magnetization or parallel magnetization, you get a resistance, so I call it this RP, like R parallel, and if they are anti-parallel, you get another resistance. So the contrast between these two resistances is called the tunneling magnetic resistance. And here, the name is tunneling, is because you have tunneling to produce a structure because you have here an insulating barrier, okay? So GMR was good, but when they came TMR, which actually is much larger than, nowadays much larger than GMR. I will show you a figure about that later on, but it's much larger. That's why we're going to focus on TMR. So you can store information with these devices. So you can have, let's say, if you have parallel, you have a low resistance state, you can say, okay, this is my 1, and you have anti-parallel, you have a high resistance state, you can say, okay, this is my 0. So 1 and 0 just mean low resistance, high resistance, or parallel configuration, anti-parallel configuration. Okay. So this tunneling magnetic resistance effect actually was discovered even before GMR. So it was discovered in 1975 by Julier. Did some experiment in this iron, germanium, cobalt magnetic tunnel junctions. And okay, so here are some of important facts regarding the developments of these structures. And since the TMR effect, after that became larger than the GMR, so all the devices that used to use GMR were substituted by TMR. So by 2004, by 2004, the TMR started to replace, GMR in the devices. And nowadays, you can find this in everywhere. So in sensors, memories, these magnetic random access memories, but mostly also in sensors. So if you want to distinguish easily between these two states, 0 and 1, you will like this contrast between low and high resistance to be large. So you want to maximize this TMR ratio, and the TMR ratio is essentially given by this expression here. So it's, by definition, is the difference between the resistance in the anti-parallel configuration and the resistance in the parallel configuration normalized to the parallel configuration. So Julier made a model for that. So in this Julier model, what you have is the following. So you have different density of states for spin up and spin down because you have an exchange field, and so the bands are shifted. And if you are in the parallel configuration, so all the spins, all the particles that are here at the Fermi energy can tunnel into the other side. So you get a big, a big transmission. And the other part, just only one part goes into the other side. But when they are anti-parallel, so you get smaller size on both sides. So actually, from this figure, it's a little bit difficult to see because the scale is very small. But I will show you now an extreme case in which, let's say that you have only one band. So that this spin splitting is so large that at the Fermi energy, you have only one spin species, okay? Like, let's say, if I have my bands split here, and let's say that now my Fermi energy is here, then I will have only one band at the Fermi energy, okay? This happens in the so-called materials that are called half metals. And you can see it easily now, okay? So if this is a half metal, you see that spin up can go here because, well, there is a space for it to go. But if they are parallel, but if they are anti-parallel, there are no states for this spin up to go into the other side. So in this anti-parallel configuration, the current will be 0. And in the parallel configuration, the current will be whatever it is, the maximum, okay? This is an extreme case, but it can happen for half metals. All right, so what is the idea of this model developed by Julier? So the idea is the following. So you have a model Hamiltonian, and this whole model Hamiltonian have three contributions here. So the Hamiltonian of the left electrode, or the left lead, the right one, and the tunneling one. So what you look now is at the rate. So to calculate the current, you look at the rate of how of electrons going from the left electrode to the right, let's say, like this one, for a given spin. And this rate you can calculate it by using the Fermi golden rule, which essentially is taking this matrix element between the Hamiltonian, the tunneling Hamiltonian, and the wave function on the right and on the right and left. And then we have here the distribution function, which tell you the occupancy of the electrons of the levels in the left electrode and the emptiness of the right electrode. So for electron to go from left to right, this leveling or this state in the left has to be occupied and have to be empty in the right because of the Pauli principle. Okay, if it's occupied in the right, so electron cannot go there. All right, so this is essentially this product. This is probability essentially of occupied in the left electrode and this empty in the right electrode. And then we have this delta function, which essentially gives you the conservation of energy. And B is the voltage. Of course, to have a current, I have to apply a voltage, right? So in the notes, I actually, you will see the notes later on. But in the notes, I have calculated this step by step. So I just will tell you what is the result of this TMR. So essentially, you calculate the currents. You go to the linear response regime, assuming that the voltage is small. So you expand this current in voltage, and you keep only the linear term in the voltage. So you get current equals something times the voltage, and this something is, what will be this? Sorry? So current equal to something times voltage. What is this something here? A resistance, if I remember the Ohm's law, this will be 1 over R. So what is 1 over R? Conductance, okay? So I will have then the conductance times the voltage. So I can then find the conductance from this equation and use it in my definition here from the tunneling magnetic resistance, TMR. So I can put it in there and then see what is the TMR. And again, so I will skip the result, but the calculation, but all the details are step by step in these notes that I will make available. So what you get essentially is this expression here, which is given by the product of this spin polarization of the density of states. So J is the density of states of G is the density of a state, and J is L, L for the left electrode, R from the right electrode, and you have the polarization of this density, the spin polarization of this density of a state. As you see, you are taking here the difference between density of a state for a spin up and a spin down. Okay? So essentially, the TMR, you see that is related to this spin polarization of the density of states. And you have a few conditions that are interesting. One of them is that, of course, if you want to get some TMR, you will need to have spin polarization of this density of states in both electrodes. So meaning the product of this must be different from zero if you want TMRs. If the spin polarization of density of a state is zero in one of the two electrodes, then you don't get TMR. So there is no contrast anymore between parallel and anti-parallel. Okay? Now, if they are perfectly polarized, then you get, so this will be 1 here, you get something divided by 0, you get a huge TMR, like infinite. Okay? Now, this model has a drawback, and the things, I didn't go into the details, but in the model, what is assumed is that these elements here are constant. They don't depend on spin, they don't depend on K, and then it made the calculation easier so that you can get this easy expression here. To overcome this drawback, so Slonczewski introduced another model, and in this model, you really take into account the transmission probabilities for a spin up and spin down, and so on. Again, the details of the calculation are in the notes, but it's a typical, it's just essentially it's a tunneling problem that you may have in quantum mechanics. It's just tunneling through a barrier. The only difference now that you have two spins, you have to take into account that, but it's the same procedure. You build the scattering states in the left region, in the barrier region, in the right region. You apply boundary conditions, you get a system of equations, and you solve for the transmission coefficient that, for this specific case, you can find an approximate relation is given here, and then you can calculate the transmissivity from these transmission coefficients. It looks very nasty to, you see, very complicated, a lot of stuff in there, but it turns out that you actually can rewrite it in a form that is similar to this Euler equation. The difference here is that you have this cosine phi. Cosine phi is actually the angle between this magnetization in the two electrodes. So if you want to just compare parallel to anti-parallel, you will just put phi equal pi, because then you will have the antiparallel will be with phi equal pi. Okay? But otherwise, so you can see, independence of the angle between these magnetizations. And then you get the same, you get, again, something here like is like, this spin polarization of the density of a state. This here is exactly what we have in the Euler formula, but then is, have this extra factor, which is actually taking into account the details of the barrier. For instance, you look at this QF, it contains this potential, which is the height of the barrier. So you can calculate this TMR, independence of the height of the barrier, and so on. Here is, I make a couple of plots of how this TMR in, percent for different barrier heights. So 0.1 electron volt. So of course, as the barrier becomes larger, you may expect that the effect will be smaller, but it's non-monotonic. You can see here that it's actually non-monotonic. And of course, you get the maximum contrast when you are comparing parallel to antiparallel, which is the situation here of phi equal pi. Okay. So here is, this dependence as a function of the height of the barrier, and these dots here are, some experimental values for some materials. So this TMR effect is actually very large, and here is, for instance, a comparison of TMR for different. So it depends very much on what is the character of this barrier. You can use I think the first magnetic tunnel junction that were built, they typically use aluminum oxide like a barrier, but aluminum oxide is amorphous material, so you have a lot of disorder in there, and therefore the effect is not so large. But if you use MgO, which is it's a crystalline structure, so it's very good, and you have not very little disorder, so you can actually increase this effect a lot. And so by 2000 something, it was like between 400-500%. Here I have a peak in here, so I don't know actually nowadays how much is, but I suspect that it's about 700-800%, the maximum that you can get for the materials we know. Okay? So very quickly we go to this tunneling anisotropic magnetoresistance. And till now we see this, we see that we have that we have different resistance independence of the junctions of the ferromagnets or the leads have a configuration that magnetization is parallel or anti-parallel. And it actually look like this, polarizer, like optical polarizer, in the sense that the first ferromagnet, what does is just polarize the current into the spins into the direction of the magnetization, and the second just analyze. So it's like the analyzer, and it allow the current to go easy or not, independence of this angle between them. It's exactly, the analogy is very good, because here also depends on the angle between this, between the polarizer and the analyzer, where here also depends on the angle between the magnetization in the left and right electrode. Now you need two electrodes here, so the question is, what if we have only one ferromagnetic layer? Will I observe anything, any different resistance if I rotate the magnetization? So one may say that no, but it came as a surprise that actually you may have differences. And this is an experimental setup for an iron gallium arsenide gold junction. And when they measure this, so they got this result. So this is the polar plots of the resistance as a function of the magnetic field, the magnetization orientation, for two different biases. And you see this. Actually, the people that did this experiment, I was a postdoc a long time ago, and I changed my field to spintronics. I was just studying spintronics, and I have made this plot for myself of the spin orbit field. So the experimentalists, they didn't know. They were very puzzled for this effect because they didn't expect any difference. And I think they were like 6 months or whatever looking for this. And once I was invited to the seminar they have, or the group meeting they have, and just, I saw this, and a week before that I have made some plot of the spin orbit field, which looks like that. And I said, well, this is the explanation for that. And so I did the theory for that, and actually, so you see the dots are the experiments, and the lines are the theory. I have a fitting parameter here, okay? Because I don't know, in this case, I didn't know what is the amplitude of the rush of spin orbit coupling at the interface. But by fitting only these parameters, you can fit all the curves, okay? So only one fitting parameter, you can fit everything else. Anyway, so why this working here? So it's, and the reason is, if you look at the interface between iron and gallium arsenide, so you can have this couple of structures here. They have very similar energy. So in practice, you probably have at the interface, some regions have this structure, which is arsenide terminated, arsenic terminated, or gallium terminated, okay? But both of them have the same structure, this two-fold C2V symmetry, which is the same symmetry that you have Raj van Dresselhaus at the same time, so the two of them. So some years later, we did actually extract this spin orbit field from first principle calculation, and they look, it depends on which region of energy you look, but in some region of energy, they look like Raj van Dresselhaus, this linear, but if you go to higher energies and you get higher momentum, so this cubic and all the higher order terms play a role, so you start to get these butterflies, so they look like butterfly. We call it spin orbit butterflies. So why do I have this different or this anisotropy in the magnetoresistance when I rotate the magnetic field? So an easy way to see that is if we plot here the spin orbit coupling field. So this is the vector field of the spin orbit coupling, and this is the strength, right? So the red line. So if you have a magnetization in this 110 direction, you see that the main contribution, the largest contribution, is perpendicular from this spin orbit field. Is perpendicular. So it's from this Slonimsky model, we know that the magnetoresistance depends on the angle between the two magnetizations. Here I don't have two magnetization. I have a magnetization and I have a spin orbit field. Okay. So if the magnetization is in this direction, then the resistance is going to be large because the magnetization is perpendicular to the large spin orbit field. If the magnetization is in this direction, then it's parallel to the large spin orbit field. So it will be, the resistance will be smaller. And that's what you see here. So smaller resistance, larger around this direction, and larger in this direction. Now, if you remember that I can flip this, right? So if I change, if alpha is larger than beta, it will be, let's say, like that. If alpha is smaller than beta, then I flip the axis. Now, so, these two may look different, but they are the same, just the axes are different. So here, the x-axis is 110, and the 10, but you rotate them, so you see they are the same. Now, what happened here is that you are applying a bias. With this bias, so you are, you're essentially shifting the wave function. You are changing alpha when you apply this bias. So you get from a situation that alpha is larger than beta into a situation that alpha is smaller than beta by the bias. So then you are just flipping this anisotropic behavior. Okay, so I will skip the math of this. So there is a very simple, actually, phenomenological model to understand what is this angular dependence of the tunneling anisotropic magnetoresistance. And actually, this is a very nice method. It's very simple, and it works. I have applied this for anything: semiconductors, magnetic material, superconductor junction with superconductors, and it always works. So And the idea is very simple, okay? So you have the transmission is a scalar function, and in the system now you have only two preferential directions, the magnetization and the spin orbit field. But the transmission is a scalar, so the only way you can create, build a scalar with two vectors is just essentially the dot product, or the cross product square, but you can decompose this again in dot products. So what you do then is expand this function into powers of this dot product of magnetization with the spin orbit. Okay? So up to second order, this is what you get here. Okay? Now you have to make the average over this K parallel. And now you see when you make the average over K parallel, this goes to 0 because this is linear in Kx and Ky, so the function is asymmetric, it's odd in K, so it goes to 0. You end up with something like that. And then you work out here this alpha, the W with alpha and beta, and you see which matrix, which of these averages are 0, which of them are equal. It's a little bit of math there, but it's simple math actually. And then you end up actually with this expression here, that the conductance have an isotropic part, which don't depend on spin orbit coupling, and this anisotropic part, which depend on this cosine of 2 phi. And you put this conductance in the form in the equation for the TMR, you just get this. The TMR is proportional to the product of alpha, beta, and the cosine of 2 phi minus 1. This cosine of 2 phi gives you this two-fold symmetry, and you see that you will have TMR only and only if you have both alpha, Rashba and Dresselhaus. So because otherwise the product alpha beta won't be 0. So if the product of alpha and beta is different from 0, then you will have this effect. And so this is actually, you could see this cosine of 2 phi dependence here. Okay. All right, so any question? Since we're on time, I will be concluding the lecture, this topic today. Tomorrow, so we'll go to superconductivity. All right. Any question? If you have any question, just. I have a little bit of the phasing with the lecture because my lectures are typically for 1 hour, 15 minutes. But here you have one day it's shorter, the other is 2. And I saw that there will be 6 lectures or 1 hour and 15 minutes. And it's not the case. So I probably won't be able to cover all the things that I promised. But I will try to get as far as I can tomorrow. At least the important things. All right, so. So if there are no questions, so it's concluded. All right, so.
No question. Or you want to discuss this next time I didn't take it?
Right. Or tomorrow.
Okay, thank you.
Yeah.
So you thought the course will have 1 hour 15 minutes?
Yes, there were 6 lectures, and I saw that each lecture will be 1 hour 15 minutes.
Oh.
So instead of 6 lectures, so it's like